So I want to start us off. We are now in the Math 1332 portion of the course, second half of the semester. We're rocking, we're rolling, we're having a good time. Chapter 1 is going to be all about basically reasoning and solving problems. That's the long and short of it. We'll go through a few of the different types of reasoning today. Nicole, that's a great question. Will we have to buy access to MyLabs Plus for this new course, or does it transfer? Nicole, it should transfer. It has in the past. I've been told it does. It should just be once we are able to start accessing MyLabs Plus, which will be the 19th, a week from today, yesterday rather, a week from yesterday. It should just automatically remember that you'd already purchased access for Math 0332. And so, yeah, that's the plan. If it doesn't for some reason, let me know, but that's how it's worked always. So it had darn well better, because we buy a special textbook that should cover, everything. So good question, very good question. Not that other questions aren't good, but that was a very one that is easy to overlook sometimes. Great question. So that's going to be kind of our concern right now today with Chapter 1, reasoning, solving problems. Chapter 1's pretty easy. Chapters 2 and 3 actually get a little bit weird, and it's going to not resemble a math course for a little while. There's going to be a little bit of time where you're like, are we taking math? I don't see any numbers. I don't see any dividing things and stuff. And but yes, actually it is math. In fact, chapters 2 and 3 are really cool. We learn about set theory and we learn about logic, and that's where I love it. And you figure out that math is not all about numbers. Very little is it about numbers. So we're going to start with some basic stuff. We're going to talk about deductive versus inductive reasoning. That's where we're going to start out. Now, the first type of reasoning, deductive reasoning, that we're going to look at. Deductive reasoning draws logically necessary conclusions from a set of hypotheses. That's the whole kind of goal of deductive reasoning. And when I say logically necessary, what I mean is it's 100% guaranteed according to the rules of logic. It's not something that your opinion can affect. It is hard-nosed and related to logic. Of course, there is an entire field concerning the validity of logic called metalogic. And we're not going to go to that level. We're going to assume a few certain logical principles are just true. Of course, we do that with all of math. We assume there's a few things in math, the number line, one number being greater than another. We actually assume that to just be true. Believe it or not, there's actual mathematicians who experiment with that, take away that kind of assumption, and things just get kind of wild. So an example of this, if I make it to school on time, I did not wake up late. So this is a basic idea. If I make it to school on time, I did not wake up late. Let's assume this to be true. Now there's other things that could make you late, but we're just going to make this assumption that it is true. If we are assuming that this is true, there's at least one thing that that must be logically necessary from this. And that's going to be, if I wake up late, I will not make it to school on time. This logically follows. If I make it to school on time, I did not wake up late, or I must not have woken up late. If we assume that's true, then the flip side is, well, if you're going to wake up late, then you're not going to be able to make it to school on time. This is actually a case of something called modus tollens, also known as the contrapositive. And it's logically necessary. This second part here, the conclusion we drew, is true no matter whether we like it or not, assuming that certain rules of logic, namely modus tollens, does not falter or it does not fall away. So that is kind of cool. Of course, it gets a lot more complicated than that. And what we're going to do is we're going to investigate in chapter 3 logic. We're going to look at logic carefully. We're going to look at things called truth tables. And we won't quite go into verifying truth of things, but we will talk about the symbology of things and we will do a little bit of statements. So it is going to get kind of interesting when we get to there. So you have deductive reasoning. That draws a conclusion that must be true. It must follow. It's 100% guaranteed. But then you have something called inductive reasoning. And what inductive reasoning does, you can't say it's guaranteed to happen, but inductive reasoning draws likely conclusions from certain hypotheses, from a set of hypotheses. Notice that word likely. That's kind of the key word there. You can't say it's guaranteed to be true, but maybe you could say, maybe it's 90% true, 80% true. If you go on and take a statistics course, you might even be able to compute certain probabilities in somewhat limited cases to a T. So inductive reasoning is actually kind of the more interesting of the two. But notice it's not 100% guaranteed like deductive reasoning. But inherently, that makes deductive reasoning a lot harder to do because it's a lot harder to give a guarantee of something. Inductive reasoning, you can there's a little room for fudging and error. You also inherently agree that it's possible you're wrong. For instance, if you're a sports gambler and you think there's a 90% chance, who's the best team right now? Maybe Kansas City? Well, they just lost, didn't they? Maybe you think there's a 90% chance that the Baltimore Ravens are going to win. Well, you inherently understand that if you go place a bet on the Ravens, you could lose your money, but you can't be upset about it because you were taking a risk. You knew there was a chance. You're just going with what you think is the most likely outcome. So deductive reasoning inherently has error built into it, or it has the possibility of being wrong or mistakes could happen. And you can't blame yourself. You made the best decision you could with what you knew at the time. You can't predict the future perfectly. An example of this, a very simple example, is I have woken up at 6:30 a.m. every day for the past 2 weeks. Maybe you got to wake up for work, school. Maybe you only have to wake up during the Monday through Friday at that time, but your body just naturally wakes you up at that time on the weekend, even though you stayed up till 3 o'clock the night before. I've done that plenty of times. And I'm like, why am I getting up at 6:30 in the morning? I'm allowed to sleep in today. It's a Saturday. I hate you, body. So I'm going to eat a lot of pizza today and drink energy drinks and, get right back at you, which is exactly what I'm doing right now. Not the pizza part. I wish. So anyways, let's say this is true. I've woken up at 6:30 every day for the past 2 weeks. Let's assume this is true. This is just called the hypothesis. This is not a conclusion we're drawing. It's a piece of information we're putting forward and we're going to say it's true, or we're going to assume it's true. Then if I have woken up at 6:30 a.m. every day for the past 2 weeks, then I will wake up at 6:30 a.m. tomorrow. Notice how this is not guaranteed to happen. What? Just because you woke up every day at that time for the last 2 weeks, what if you just started a break? What if you work a job where you work 2 weeks on, 2 weeks off, and you work like 80 hours a week when you're working on, and then today just started your 2 weeks off so you can sleep until 10 a.m. or something like that? There's all kinds of things that could happen. Or you're just really tired and you sleep through your alarm. There's no guarantee that you're going to wake up at 6:30 a.m. tomorrow just because you've done it the past 2 weeks. But what we're saying is this is a likely conclusion based on no other information. If you don't give me any other information, this is my best guess, and I think this is going to happen, that I'm going to wake up at 6:30 a.m. tomorrow. So this is what inductive reasoning would call. They look similar. If you just look at these, you would think they're both the same form of reasoning, but technically they're not. So that's kind of interesting. This is likely to happen, but it's not guaranteed. You could accidentally wake up at 10 a.m. tomorrow, and that's just life. One other quick note I'll make is that inductive reasoning usually goes along with pattern problems. If you see a pattern of things happening, you're going to assume that that pattern is going to persist. This is true if you look at the animal kingdom. If you have an animal who's normally a prey, maybe a zebra is a prey to a lion. If they hear a rustling in the leaves, or if they hear something that's like or a growl, they hear something that is normally a telltale sign of a lion, there's no guarantee it's a lion. It could be a different animal that's not a predator to them. But they're going to make the assumption that it is a lion. They do this in their head without realizing it. It's instinct. And they're saying it's likely a lion, so I need to get the heck out of here. I need to run away, get a head start on the lion. So something like that is inductive reasoning is actually what goes along with our instincts, because we're saying this is likely to happen. It's not guaranteed, but your mind just says, okay, I'm hitting a skid on the road, which is never fun. So you're going to try and do what you think is your best chance of surviving, which is supposed to be to steer into the skid. It's not guaranteed, though. It doesn't mean you're going to get out of an accident, but it is your best chance, or it's your most likely thing. So inductive reasoning usually goes along with pattern problems. Here's a bit why. Let's start with a very easy pattern. 3, 6, 9, 12, 15, and then we put a little underscore there. We put a little underscore there, and so the implication is fill in the blank. Well, this appears to be what we just call a simple arithmetic sequence. Arithmetic just means that it's changing by adding the same number as before each time to get the next value in the sequence. And it seems pretty clear we're just adding 3. Start with 3, add 3, add 3, add 3, add 3, and that's accurate. So you're tempted, and usually that temptation is fine. You're tempted to put an 18 there because that's 3 more than 15, and that seems like it would be the next step in the pattern. What you're doing without realizing it, you're assuming that pattern to go on. You're assuming that pattern, let's use better phrasing than that, will persist. Perhaps, though, that is not guaranteed. So this is actually inductive reasoning. You're saying it's likely then that the next term in the sequence is going to be 18 because, hey, that's just the pattern that has been forming, that it's an arithmetic sequence where we keep adding 3. But it's not guaranteed, is it? Now, maybe if the problem says assume the pattern continues, maybe you're safe then. But it's always possible that you could just be totally outright wrong. What if these numbers were the number of students you see walking into school in packs, in groups at the beginning of class? So maybe it's early in the day and you see the first 3 students, they come together in a group, and since we're going to assume they're high school students, every single one of them is on TikTok, doing some kind of TikTok thing. Then you see the next group later on of 6 students, and they're all on TikTok, of course, but they come in together in a group. Then you see a group of 9 students come into the school, every single one of them on TikTok. Then you see, in fact, some of them have 2 phones, so they can be watching 2 TikTok videos at the same time. Then you see another group of people of 12 students coming in together, all on TikTok. Then you see a group of 15 coming in together. You're tempted to say, well, it keeps going up by 3 at a time, but that could just be mere coincidence. That could have just happened to be that way. And then all of a sudden it turns out, oh, now the next group I see only has 10 people in it. And of course they're all on TikTok. But the point is, if you see patterns in the wild, they're not guaranteed to be following that. You might just be seeing a coincidence happening and you're going to assume a pattern continues, but it doesn't. You're going to assume that. This is actually a really, really, really big deal when you get to statistics. If you take a statistics course, you might have this idea that statistics is all about predicting the future and that statisticians must know how to win the lottery or they must know this or that. No, that's not true at all. Statisticians just apply probabilities to things. They think this will happen with this probability, and they just try to make the best decision. And they know how to utilize data the best, but that doesn't mean they can perfectly predict the future. Nobody can. Anyone who tells you that they can perfectly predict the future is somehow trying to swindle you out of your money. I promise you that is going to be the case. In almost every single case, someone is just trying to swindle you out of your money. Oh, I predict that, whatever, that you're going to be a millionaire someday. Or it's fun. It's fun to do it. Maybe it's fun to go and get your palm read. I don't know. That's not something I do. But maybe you enjoy doing it, but take it with a grain of salt. If they tell you you need to leave your husband right now because he's a jerk and nothing in your life has said he's a jerk. In fact, he's a wonderful, sweet man. Don't believe someone who's predicting the future. They're trying to just shock you and get your money. That's all it is. So nobody can predict the future. Thus, you can't say this pattern in particular is guaranteed to happen. It could be pure coincidence. And that is huge in statistics. That is a major issue in statistics when you get down and granular with it. So this is kind of an interesting problem. So inductive reasoning would say put an 18 there because we're going to assume the pattern goes on and it's likely that it's 18, but it's not guaranteed. So inductive reasoning really borrows from pattern or goes along with pattern problems, but it's not. That's why it's not deductive reasoning. I can't deduce this as an 18 because deduction means it's 100% guaranteed to happen according to certain rules of logic. And then one more quick type of reasoning, and this is just kind of a preamble. This whole reasoning talk is a preamble to chapter 1. One more quick type of reasoning is called abductive reasoning. Abductive, it sounds like a new workout machine, and it is. No, it's not. I don't know, maybe someone's done that, but. And what abductive reasoning does that's a little different than the other ones, it's going to sound a little bit like it's borrowing from inductive reasoning, but technically it's not quite. What abductive reasoning does, abductive reasoning draws conclusions based on what is the simplest explanation or the simplest manner in which something can be done. If you've ever heard of something called Occam's razor, not Occam Asylum from Batman, but Occam, William of Occam was a medieval scholar. I believe he was a monk, actually, a hermit who just studied his whole life. And Occam's razor states that the most likely explanation is the simplest one. And we're getting into some really, really murky waters now. So abductive reasoning usually it says something like this. Whichever conclusion can be drawn using the least number of hypotheses or the least amount of new evidence that you have to bring in is the most likely outcome or is the outcome or explanation. So we're not going to get super detailed with this. And technically none of this talk about reasoning today is going to be on any tests or homeworks, but this is actually going to fuel our discussion of things that will be on tests and homeworks. So it's just kind of interesting. So you might hear people say, oh, I deduce this, and or something like that. And sure, that's fine. They can say that. So 3 basic types of reasoning. Now let's jump in to basically the material that we're going to cover now that will be on homeworks and the like. So I've got a nice little thing for you. Problem solving and critical thinking. And so on the surface, this is going to be the, how can I put it? This could end up being the hardest chapter of the course. In practice, it usually doesn't turn out that way. but it could, because what we're going to concern ourselves with in this chapter is trying to reason through, frankly, word problems, because word problems is where math is at. Everything else is just kind of, okay, yeah, I can solve an equation, but can you take a situation, set up an equation for it, solve that equation, and interpret properly? That's obviously a much bigger task to do. Therefore, it is something we are going to be asked to do in a math class. So that's kind of what we're concerned with in chapter 1. So estimation graphs, mathematical models. Anytime you see mathematical modeling, that's usually going to mean word problems are going to come up. So to start, we need to talk about estimation. Estimation is the process of arriving at an approximate answer to a question. Sure, that's great. You think, well, when would estimation be important? Well, let's say you're kind of bored, you're out driving, and you're worried about being able to pay all your bills this month. I have been there. I think we've all been there. It's not fun, not a fun situation to be in. So you got to sit down and you got to think about what all your bills come out to, and then you got to make sure you're going to have enough income coming in plus what you already have in your bank account or your accounts. And you got to say, all right, if the amount of money I got coming in plus my bank account is more than what my bills will be, I'm fine. If it's less than what my bills will be, I'm in a little bit of an issue. Well, if you're out driving, and which means you should not be on your phone, let me repeat that. If you're out driving and you are the one driving the vehicle, you should not be on your phone. You should put your phone to the side. I know it's tempting to just, if you're under 20, you're probably just watching TikToks. I have this weird impression that everyone like under 20-ish or so, literally their entire life is TikTok. Because, you know, I see kids that are a little bit younger, teenagers. I have some nieces that are 16, and pretty much every time I'm around them, they're literally on TikTok, literally the entire time. Literally, not even doing TikToks, they're just watching them. And you try to ask them a question, they just trail off. And now I sound like an old man because I'm like, whatever happened to good old-fashioned conversation and talking to people when you're with them? But I actually do kind of believe that, as much as it might make me sound old. Anyways, that's going off on a trail. Anywho, so if you're in your car driving, you're not going to be able to use your phone to do a calculator. You just want something off the top of your head. So maybe you have bills that are $23.56, and then you know your power bill happens to be $110.52, and then you know your water bill is $59.62, and then you know your Hulu and the Netflix and all the other things. All of them are usually going to go out to the nearest cent. They're going to go out to 2 decimal places, and you got to add all that up in your head. What? No, you're going to estimate. You're going to round those things. That Netflix bill, $11.99 or whatever with tax, it comes out to $13.47. Round that up to $14. And in that case, it's wise to round it up to the next dollar, because if you're overestimating your bills and you can still pay them all, you know you're okay. You're playing it conservatively. So yeah, if you're in your car, if you got to do something quick off the top of your head, it's important to understand how to round numbers. Rounding numbers is going to be incredibly useful, because it lets us make quick and dirty estimations off the top of our head. Another reason that estimation is useful that's not really written here, excuse me, another reason it's useful is that you can verify whether or not something makes sense. So let's say you bust out your calculator. Let's say you are able to sit down, you're at your desk, you're not in the car driving, you've already watched 3.5 hours of TikTok, so you're ready to take a 10-minute break before a 7-hour TikTok session after that. And you're ready to calculate your bills, calculate your income, make sure you have enough to cover your bills. Even if you have a calculator, let's say you crunch all the numbers and your bills come out to $22,857.32 this month. Ooh, you probably made a mistake. So you can, if you had already done an estimate in your head, oh, my bill should come out to about $350 this month or $1,000 this month, give or take a little bit. If you've already done an estimate off the top of your head, you can quickly identify something that's nonsense. You've clearly made a mistake when you've punched it into the calculator. So that is a very useful kind of a result of estimation. You can use it to kind of say, no, that doesn't make sense. What we're going to do is this semester, we're going to be, when we get into chapter 8, we're going to talk about finance. We're going to talk about money. We're going to talk about interest rates. And even if it seems boring at the time, it is something that is absolutely relevant to you personally. I'm even going to teach you how income tax is calculated, how your income tax is taken whenever it's time to pay taxes. And if you're earning money in this country, you should be paying taxes on it. So that's why it's important to really pay attention to that. Well, if you're buying a $200,000 house, which is a reasonable market value for a home in this area, if you're buying a $200,000 house, you plan to do a standard 30-year mortgage, making monthly payments, you got a decent interest rate, and it says your monthly payment is going to be $5 million, you probably made a mistake. Your monthly payment is not going to be $5 million. Ballpark, it's going to be closer to about $1,000 or so, $1,000 a month. Of course, you have to pay property taxes too. So, but yeah, so keep that in mind. Keep that in mind. Having estimation is useful because it gives you an idea and it can let you call nonsense, BS, on a problem. So we've actually, in the Math 0332 course, we spent some time talking about rounding whole numbers. Rounding whole numbers. So this part should not be a huge surprise to you. We've already said figure out the digit that is to be rounded. Look one digit to the right of it. If it's 5 or greater, round up. If it's less than 5, 0 through 4, round down. The only thing I might add, and I think I've shown you this, but just to be safe, if you were taking like a really ridiculous number like 5.4987716, and you wanted to round it to just one decimal place, you wouldn't say it's equal to, you'd say it's approximately equal to. You'd kind of use like a wavy equality sign. Wavy, man, that's so crunchy. And if you round it to one decimal place, you have, this is the digit to be rounded. You look one to the right, it's a 9. So that's going to round up to 5.5. But now it's not exactly equal to 5.5. These are still two different numbers, but 5.5 is just our rounded estimate for this number. So we got to use kind of a wavy equality sign. So that's all that means. So you'll see me use that just to dot my I's, cross my T's. So we should already be good at rounding. Maybe we'll just go through a little bit of a quick rehash. If we had the world's population at whatever time this was taken, 7,476,242,056. Well, you probably don't need to go out to that much. You don't have to get that specific with it. You're like, all I want is a ballpark. So you might round it to the nearest 100 million, and the 100 million would be at this 4 here. You look one digit to the right, which is 7, so you're going to round it up to 7,500,000,000, and then you could just say like 7.5 billion or something like that. There was an old joke, if you ever watched Star Trek: The Next Generation, and yes, I've watched Star Trek: The Next Generation, and so if that lowers your opinion of me, well, too bad. I like Star Trek: The Next Generation. Technically, Star Trek Deep Space Nine is probably a much better show, in my opinion. Hi, Cameron. If you have watched Star Trek: The Next Generation, there's a character on there named Data. Data, he's an android. You can go look him up. You probably recognize him from something in pop culture. And he would always, the captain would say, how long till we get to the next place, Data? And Data would say, at our current velocity, it will take 2 days, 13 hours, 4 minutes, 22 seconds, and 19 nanoseconds. And Picard, the captain, would always say Data. And what he was telling Data was just round. Just, okay, 2 days, 13 hours. So say about 2.5 days, about 2.5 days, 2.5 days. And you're golden. So that's kind of why it's important to estimate. You just want a quick ballpark. I don't need to go out this specific. This is the right answer, But sometimes being right isn't what you need. Sometimes being 100% accurate is not what we're looking for. So we'll see different examples of rounding here, of rounding that population. If you just want to round to the nearest million, then you would have to go to the 6, look over to the right, it's a 2, so you'd round down and fill out zeros the rest of the way. But we have already covered rounding in a little bit of detail back in the Math 0332 course. So all I'm going to say about it is that rounding is just a tool of estimation. That's all it is. Here's where rounding can get you into a little bit of trouble, especially for some of the finance problems we're going to be doing in Chapter 8. Rounding intermediate values that you use along the way in a calculation can create problems. It just can. So what we usually will say is, okay, let's say you're doing a problem and it wants to know what's the monthly payment for this mortgage, something like that, for a $200,000 house. And the monthly payment is going to end up being, maybe about $1,000. But if you have to round the final answer to 2 decimal places, which you usually will do that because if you're talking about money, 2 decimal places is the nearest cent. If you have to round to 2 decimal places, then any intermediate calculations and numbers you do, round it, heck, you got time, you got paper, round it to 8 decimal places as you're going along the way. And even though that's not exactly perfect, when you get to the final answer, your final answer is probably still going to be correct out to 4 decimal places. And since you only need 2, you're golden, you're fine. That's going to be my humble suggestion to you. So round intermediate problems, go way further out than you need to, but round your final answer to whatever the problem specifies. Here's a nice example of using estimation. Again, this is like if you need just a quick and dirty estimate off the top of your head, you could round things to the nearest dollar. Bread, you spent $2.59, round it to $3. Detergent, you rounded it to, it's $5.17, round it to 5. Round it to the nearest dollar. So here's the nearest dollar. Look, 1 decimal place to the right of that. And so this would suggest rounding up to 3. This would suggest rounding down to 5. And so yada, yada, yada. And what you end up with is now 3 plus 5 plus 4 plus 0 plus 9 is probably something you can do in your head. Now, here's the problem. The true total amount was $20.67. If I go ahead and just add up all these here, then and not round at any point, the true value is $20.67. So if you're at the store and the bill came out to $24.67, but your estimate told you it should have been $21 roughly, you might then say, hold on a second and see if there was a mistake done. So that's just kind of the whole point of estimating. It can help you give you a quick and dirty idea without having to spend way too much time to do it. Of course, we can all bust out our phone calculators these days and kind of do these calculations quickly. But I don't know, maybe you're driving, maybe you're in like a high pressure situation where you got to make it quick and you can only do it off the top of your head, something like that. Maybe you're at a theme park and it's busy and you don't want to get the coronavirus because it's real busy and there's tons of people everywhere. And so you're like, make sure you have enough money in your account to buy this sandwich at this shop. You might need to just do quick and dirty calculations off the top of your head because you're in a stressful area. One last thing I'll say about this. This can lead to problems. The true total was, if you add all these up, was $20.67. Your estimate was $21. So your estimate was high, which if it comes to paying bills or something, it's better to have a high estimate. So actually, this rounded to the nearest dollar in each case, I would have actually rounded up no matter what to the next dollar. So 259 would have rounded to 3, but 517, I would have rounded it to $6. 365 rounded to $4. 47 cents, I would have actually rounded it to $1. That way, all your estimates are high, and that way you know, oh, well, it came out to $23 and I have $25 in my account, then I'm okay. I'm still okay. So just sometimes you want to be conservative, sometimes you don't. when it comes to how much money, like if you have a couple streams of income, if you have a couple paychecks from different things, you work two jobs or you have an online business, sometimes you might want to lowball yourself on how much money you're going to bring in. You want to use a low estimate so that you're not trying to think, oh, I'm about to bring in all this money, and then you're on the bad end of it. It's better to be wrong, and it turns out you're actually bringing in more money than you thought than the other way around. So estimation has some quirks. Okay, so other things we can do with estimation, or just kind of general ideas of reasoning here. We can use certain kinds of graphs, a circle graph, also called a pie chart. In fact, everyone calls it a pie chart. Circle graph is just kind of maybe a more formal way to say it. It's called a pie chart because you make a circle and you cut it into pieces of the pie. So this is actually kind of an interesting one. Let's say 200 people were surveyed and asked, what is your definition of old age? How would you define old age? Now, for me, it's if you have, what are those? You know, those little strawberry candies that you unwrap and the wrapper looks like a strawberry. And I like that candy, so maybe I'm old. I don't know. Or if you have Werther's Originals, or you watch Star Trek: The Next Generation, that might be a good definition of it. But about 32% of people would say it's a decline in mental functioning. 41, so it's your mind. 41% say a decline in physical ability, so your body. Becoming a grandparent, retiring, reaching a specific age like 60 or 70, or you don't know. That's what percent of people answered each of those responses of those surveys. So we can kind of use a circle graph to make estimates of things. For instance, if it turns out that there are 219,345,625 Americans who are at least 25 years old, and we wanted to know, well, according to this chart, 41% of them think that old age is when you start declining in physical ability. If you want to know how many Americans that was, you would need to take 219 million, blah, 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 this number, and take 41% of it, which means convert 41% to 0.41 and multiply. That's kind of the whole point of this. But if you're doing it off the top of your head, well, okay, I can do this one with a calculator. But if I was trying to do it off the top of my head, I would instead round 219, 345. I would round that to a clean 220 million. It's close enough. 0.41, just round it to 0.4. And maybe you can kind of do that one in your head and say it'll come out to 88 million Americans. So it's about 88 million. It doesn't have to be exactly, but it's in the right ballpark. Bar graphs are also useful. Can you use them for estimation? Sure. This bar graph is kind of interesting. This is life expectancy in the United States by the year you were born. So those born in 1950, on average, males born in 1950 will live to 65.6 years of age. Females will live to 71.1 years of age. What's interesting is that if you're born in 2000, obviously you would expect to live longer because you've spent more of your life in good medical, circumstances. Of course, there's plenty of people born in 1950 still alive today, but you have to realize there's some that have already died, or when they were born, a higher amount of babies were dying at birth in 1950 than they are today. So that kind of brought these averages down a little bit. But yeah, medical science has improved. Certain economic measures has made our life expectancy higher in the United States. But my point of this one is that males are the red bar, females are the yellow bar. And ladies, you've got us beat. You've got us men beat. Even though we're starting to close the gap here, women just are living, 3 to 4 years longer on average than men, 4 or 5 years, maybe something like that. Which is, I won't say anything about that, except that usually has to do with the fact men are likely to just die of a heart attack because we're just wired quicker. Men are likely to just pop off and die instantly. My own grandfather passed away of a heart attack at work, which is probably was his dream. He was probably happy to say he was working when he died. Heart attacks are not fun, and they affect men more often than they do women. Um, Women tend to live on a little bit longer, even after a serious medical event. Women are more likely to survive it and keep living. Men are more likely to just die of it quickly. And that's just an insurance fact. So if you ever purchased life insurance, your life insurance is going to cost more than women because a man is more likely to die in the time frame of the life insurance than a woman is. So just some interesting facts here, but this is very real. So you can use certain things to track or estimate life expectancy. For instance, estimate a man's increased life expectancy for each subsequent birth year. In other words, on average, as you're born later and later on in time, how much are you increasing your life expectancy? This is actually just a slope calculation. Look, men in 1950 would have a life expectancy of about 65.6 years. Men in 2020 would have a life expectancy of about 77.1 years. So all you did was take y2 minus y1 over x2 minus x1, and that gave you an approximation of how much your life expectancy, a male's life expectancy, increases each year longer that they put off being born. Of course, you don't have control over that, but it's just kind of an interesting idea. Every year you wait to be born, if you had control over that, your life expectancy, you're going to end up living a longer life on average. So just kind of interesting stuff. You can also estimate the life expectancy of a man born in 2030. The last part said that every year you put off, quote unquote, being born, you have 0.16 more years added onto your life on average. So if you're born in 2030, that's this is actually wrong. That's 80 years after 1950. So that's kind of where they're getting this little side calculation from. This is actually supposed to be 80 right here, but they did the math right down here. All they did was set up a linear function, y equals mx plus b. So kind of interesting. We can also look at line graphs. Line graphs are interesting. Cigarette use by US college students. So in 1982, roughly 24% of college students were using cigarettes. That probably meant smoked more than one cigarette per day on average. It declined a little bit. The Teenage Mutant Ninja Turtles probably came out with ads saying don't smoke cigarettes, or I think that was heroin or something. But then, it went up a little bit. Maybe people were more stressed. Usually people smoke cigarettes because they're stressed. And then it started to decline. This is probably due to the massive amount of medical data we've seen that shows that smoking cigarettes is terrible for your body. Obviously, it's terrible for your lungs. So you should, I'm not going to tell you what you should do or not with your life. But yeah, the medical information says if you smoke a lot over time, your life expectancy goes down, all kinds of bad things can happen. So over time, the percent of college students who are smoking has gone down. So that's all the line graph does, is it just puts a bunch of points on here and then just draws a line connecting each of those points. Find an estimate for the percentage of college students who smoked in 2010. Use the line graph. 2010 would be in between 2006 and 2014. So 2010 is probably this one. Go up to it. Oh, it's about 18%, if you can read across. So in 2010, about 18% of college students were smoking cigarettes. I bet that's even less today, like way less than that. That even seems kind of high. I just don't see a lot of cigarette smoking at all anymore. And so that right there. In which 4-year period did the percentage of college students who smoked cigarettes decrease at the greatest rate? So what we're looking for is a line that's decreasing and that is the most steepest line in doing so. And it looks like it's this here. It's decreasing because it's going down, and it's the steepest line. It's decreasing at the greatest rate, or the fastest, in other words. And that would be between, 2002 and 2006. So maybe sometime around 2002, there was a huge push in advertising from the Surgeon General or medical people saying don't smoke cigarettes. That could explain. So yeah, 2002 to 2006. In which year did 30% of college students smoke cigarettes? Well, go back to the graph. 30%, it looks like this is about 30% right here, and that would have been the year 1998. So I don't know what happened. The 90s, just everyone was smoking again. Maybe it's because they had a president who played the saxophone and people like to smoke cigarettes while playing the sax. I don't know. So yada, yada, yada. Here's one that's going to be kind of depressing. This is a depressing one. This is the cost of attending a public college. In 2000, it was about $3,349 per year just for tuition and fees. Of course, you still got to pay for your room and your board. And for some reason, board, when you're talking about room and board means food. And I don't get that. I don't get what I thought boarding would be the staying there and then you just call it food, but no, board is apparently food. So that one racks my brain. This isn't quite a fair scale. This thing should be starting at 0 because this bar right here looks like it's 10 times higher than this bar. 2016 looks like it's 10 times more than this one, but it's actually it's not even 3 times as high. So that's because this scale didn't start at 0 here, but that's fine. We can still see an increase going up. And yeah, just in 16 years, colleges has increased in price by almost 3 times. And yeah, that's very realistic. The reason for that is perhaps fairly simple economics. Economics dictates that as more people demand a certain good, well, if more people want something, you're going to jack up the price, right? Now, that's not exactly what's doing. It's not like they're saying, we're going to raise prices and steal all their money. And they, they have the Snidely Whiplash mustache and they twirl it. That's not necessarily what is happening. Instead, a specific college can really only bring in so many students. It's just the truth of it. So if one college has way too many people trying to get in, well, they're going to have to reject some people. It's just because they don't have the resources for it. And one way you can reject them is, okay, you have them apply to the college and you just only take the top whatever percent of them and you tell the rest, sorry. But another way to do it is you just raise tuition. And unfortunately, that means you're going to have to price some people out. But really, as a college, you have no other option. And you're also going to have to raise prices because if you're dealing with more students, you're going to have higher costs. And so you might, at least in the short run, you might have to raise prices. Also, the cost of everything is just going up because of inflation, and inflation is also one of the major causes of inflation is just increased demand for goods over time. So it's not malicious, I wouldn't say. It's not that colleges are evil and just want to charge more because they're all greedy. It's actually really because more and more people are seeing the value of a college education when it comes to getting, better, higher paying jobs. And that's just the truth of it. I assume everyone in here is in college because they want to get a better job than they have now, or they want to get a good job someday. And yeah, there's nothing wrong with that. That's exactly why most people would go to college. Personally, I do think there is a value in just being educated, period. Even if you take a certain class and that specific class doesn't appear to immediately increase your chances of getting a better job. That class, on the other hand, could teach you something, a skill you never knew you were good at. So it could completely change your career path, or it could just mean you found a new interest. And think about it. The whole reason you're alive is not just to work and make money. You want to work and make money to give yourself a comfortable life. So frankly, when you're not working and when you're on your free time, you can pursue your interests. You can spend time with your family. And if you get a broader range of interests just from going to school, that is enriching in and of itself. So that's kind of the standard spiel, but I do believe it. I really do believe that. So yes, college tuition has gone up. The average yearly increase between 2000 and 2016, look, they just calculated a slope again. In 2016, it was $9,410. In the year 2000, it was $3,349. So just figure out how much it went up in those 16 years. Oh, well, that's the difference here. And divide by the 16-year difference between the two. And on average, it went up about $379 per year. $379 per year, which doesn't sound high, but in just 16 years, it triples the price, almost triples the price of a college. You could even make then a linear equation out of that. You could say starting with the year 2000, it was $33.49, and then every year it's going up $379 on average times the number of years you want to talk about X. And that means you can predict what tuition will look like in 2020, which was not on the chart here. The chart ends at 2016. Using that chart, you could say, well, 2020 is 20 years after 2000, so X is 20. Plug it into that equation, and now we're supposing that in 2020, tuition is going to be about almost $11,000, $10,929. So we're just using estimation. We can use graphs and charts to get an idea of how much something's changing, and then we're making an estimate. It's not guaranteed to be exactly $10,929. That's just our best guess. It could come out to $10,500 or $11,200. There's other factors at play that we're not necessarily bringing into the mix or that we're not seeing. We're doing kind of an after the fact calculation. So that's it for the first section. Again, this week's kind of a lame week, or dead week kind of, because we don't technically start 1332 until next week when it comes to MyLabs Plus. So what we're gonna do is we're gonna take it a little easy today. We're gonna call it for today. I'm going to take, attendance here.